Hi, this is Miss Logan. Today I'll be covering Chapter 6, which are the applications of Newton's laws. So I'll be talking about friction forces, spring forces, and when we have forces that are attached. Frictional forces are something that we deal with every day and actually help us out a lot. Friction has its basis in surfaces that are not completely smooth. So if we think about a desk, if we rub our hands on it, it seems like it's smooth. However, at a microscopic level, it is not. So this gives us friction between that desk and whatever is on top of it. Now, we actually have two different types of frictional force. So kinetic friction is the friction experienced by surfaces that are already sliding against one another. Most of the time, though, we'll be talking about static friction. So this is a friction that depends on the normal force and is the amount of friction needed to get something to move. So if you think about it, if you're about to push a box, it's often harder to get it moving than when you're actually pushing it. Okay? This is because static friction is always more than kinetic friction. Now, what is the equation we're going to use? We have F equals mu times normal force. As a reminder, normal force is often mass times gravity. And if something's at an angle, we'll have to figure out what that normal force is at the angle. Mu is always less than 1. This is our coefficient of friction. It's always less than 1 because it's a proportion. It has no units. And a good way to check yourself when you're looking at answers, if mu is less than 1, you're good. So static frictional forces keeps an object from starting to move. So like I said, if we think about a heavy box that's sitting on the ground, it takes a lot more force to start pushing it than the force when you're actually pushing it. So the static frictional force has a max value, but may take any value from 0 to the maximum depending on what we need. Okay, and this is showing here that we need an increased force as we want this to move, and after we start moving it, it's actually going to be less for our kinetic force. So something to think about as you're getting answers so you can actually check yourself. All right, so our second topic is strings and springs. Okay, so when we pull on a string or rope, it becomes taut, and by taut we mean that it's pulled all the way. We can't really, it's not loose at all. Okay. We actually call this the tension in the string. So the tension is always in the direction that it's being pulled. So for in this instance, the hands are going towards each other, so my tension is going towards the center of the hands. However, over here, my rope is being pulled off to the side, so my tension is going to the right and the left. Something really important to think about when we set up problems. So another thing that we're going to be looking at and using a lot is a pulley. Okay, so a pulley is going to change the direction of tension. Okay, so for instance, this man right here is starting to move this box. Okay, pulleys are simple machines that help us easily move things. Okay, so the tension is starting to go up because that's the way of the movement. Now the equation we're going to use is Hooke's law. This looks very similar to our friction law. So Hooke's law says the force equals K, which is the spring constant, times X, or delta X. And this is always in meters. So this is going to tell us the force based on how much something is stretched or compressed. So let's look at some sample problems. A box with a mass of 40 kg is dragged across the carpet with a force of 40 newtons. What is the coefficient of friction? So we have my force of friction equals mu times force normal. Don't have any angles involved. I'm solving for mu. So we have mu equals force of friction over Fn. Now, remember that force normal is actually my mass times gravity, so we can actually kind of just put everything into one equation to make life easier. So my force of friction is 40 newtons, that's how much I'm pulling with, and then my mass is 30 kg times 9.8. So for my final answer, I'm going to get 0.136, and it's a good check because it is less than 1, which is what we'd expect. Second problem, a string is stretch to 10 centimeters, so my delta x is 10 centimeters, but I mean this in meters, so that's 0.1 meters, with a force of 30 newtons. What is the spring constant of the spring? So we have F equals kx. We're solving for k, so k equals F over x. Here I can plug in my numbers, so 30 over 0.1. So for my spring constant, I should get 300, and my units are newtons over meters, because I have force over a distance. Last thing we're going to talk about is translational equilibrium. Now, something important to remember in this chapter, that a lot of things that we did come back from chapter 5. Okay, so when an object is in translational equilibrium, the net force is 0. So this means that it's still, and it's perhaps in the air, something's pulling on it. Okay, this allows us to calculate unknown forces. So once again, remember, this is a vector. So we need to break everything up into fx equals 0 and fx equals y equals 0. This is so important when we start doing problems. So what are some situations we're actually going to see this? So for instance, when we have forces acting on a pulley, we have tension that's going up and tension that's going down. Now, if we expect that this is in equilibrium or constant velocity, we know that the sum of all of these is equal to 0. Same with here. We have our tension 1 and then our weight, so that's also equal 0. Now, we're often going to see this in connected objects, which I showed before, but this looks a little bit different. So when forces are exerted on connected objects, their accelerations are the same. We did see this last chapter during the flipped lesson. If there are two objects connected by a string and we know the force and the mass, we can figure out the acceleration and we can figure out this tension. So when we do these problems, we need to make sure we treat each box as a separate system. So for box 1, it has this force here, which is the force we're pulling with, and then it has its tension on the other side. I also have the tension on this side because it's being pulled to the right. Now, if we have pulleys, we're going to see things work a little bit differently. So if we have a pulley, it's easiest to have the coordinate system as it's shown here. Okay, so like it said on the previous slide, we always treat the different masses as two separate entire situations. Okay, so this mass 1 over here, I have everything going on the x and everything going on in the y. So this is a standard coordinate system. Let's talk about why we switched it on its side. Well, remember, my string is connected. Okay, so we want to keep those on the same exact plane. Okay, it's just going to really help us out with our calculations. Because these are connected, they're still in the x coordinate system. However, they are turned to its side. So when we work on problems like this is an important thing to think about before we set them up. Okay, so let's look at an example to figure out the acceleration on this system. Now, the first thing I need to do is read the problem and look at what forces are involved. So a pulley with a mass of 5 kilograms and a mass of 8 kilograms move along a frictionless pulley. So we're going to figure out the acceleration of this system. So I have the weight of M1, which is 5 kilograms. So we have mass times gravity. And then I have tension that's moving up. On the other side, I have my 8 kilogram mass with my mass going down, my weight, and my tension going up. So it's important to remember that we need to think about, just from knowing the situation, which way is this going to move. So mass 2 has more mass and weighs more, so it's actually moving this way for acceleration. So this is going to be important when we set up these two different situations. So like before, we're setting these up as two separate entities entirely. Okay, so we're still using the total of F equals mass times acceleration. And let's look at mass 1. So we have Ft, which is positive, minus m1g. Why is it minus? Well, it's going down. So then we're going to have equals mass, and then our acceleration for this guy is going to be positive. Really important to make that distinction. All right, so for the other side, I have my force of tension minus m2g, because it's going down, equals mass times acceleration. And now we have negative because it's going down. So this initial setup is very important. Now we know that Ft has to equal Ft. And we're solving for acceleration, so let's start to plug some things in. Okay, I'm going to rewrite these equations so that they solve for Ft. Now it's also really important, you'll notice that I added in my m1s and my m2s. That's really important distinction as we start working on these problems, because it can get a little bit tricky if we don't have them written in properly. All right, so at this point I can set them equal to each other. So I have m1a plus m1g equals m2 times negative a plus m2g. Now remember, I'm solving for acceleration, so we need to get all my accelerations on one side and everything else to the other side. So I'm going to move this guy over here and this one over to the other side. So this is going to look like m1a minus m2 negative a equals m1 plus m2g. All right, so at this point, we need to get A by itself. So this is probably the most complicated setups that we'll actually see in this class. And it's really valuable, though, for the algebra. And the algebra just kind of stays the same most of the time. All right, so now I need to solve for A. So now on my other side, let's solve for A. So I have A m1 plus m2 equals g m2 minus m1. So I'm taking out the g from my right side, taking out the a from my other side. I'm solving for A, so my final answer, before I plug in numbers, will look like this. At this point I can plug in my numbers, so gravity is 9.8. I have m2, which is 8 minus 5 over 8 plus 5. So for my final answer, I'm going to get 2.26 meters per second squared. So make sure you took notes during this flipped lesson since it covered the entire chapter. We'll be going through problems in class and by yourself working through some of these situations.